Change of state. To better understand change of state, it's worth taking a close look at about what is happening on the atomic scale when energy is applied to a substance. We have already seen what determines whether a substance is solid, liquid, or gaseous is the way atoms and molecules are held together, so the state of matter depends on the amount of energy inside the substance. When a substance is heated, the amount of internal energy increases and the atoms or molecules move faster. Kinetic energy of the atoms increases. This raises the temperature of the substance. The figure below helps to understand what is happening. When a solid body is heated, its temperature rises. The molecules gain energy and vibrate more. Their vibrational kinetic energy is increasing. There is very little change in the mean separation between the molecules. Now let's see how changes of state works. Transferring energy to or from a substance can change its state. Heating a substance in the solid state will cause it to melt. Melting occurs when a solid substance turns to a liquid. Continued heating will cause the substance to evaporate or boil. It occurs when a liquid turns to a gas. Some substance in the solid state can change straight to the gas state. This process is called sublimation. This process occurs when energy is added to a substance. But you know the process can be reversed, so when the substance is cooling, the process is reversed. A substance in the gas state condenses when it is cooled. Condensation occurs when a gas turns to a liquid. Continued cooling causes it to freeze. Freezing occurs when a liquid turns to a solid. We can show how the change of state occurs using graphs. A heating curve is a graph showing the temperature of a substance plotted against heat, that is, the amount of energy it has absorbed. To better understand the physics of phase change, suppose a 1 gram ice cube at minus 30 degrees Celsius is in contact with a heat source. The ice cube is in a container held at constant pressure. Suppose this input of energy turns the ice to steam, water vapor, at 120 degrees Celsius. The figure below is a plot of the experimental measurement of temperature as energy is added to the system. We examine each portion of the curve separately. Part A. During this portion of the curve, the temperature of the ice changes from minus 30 degrees Celsius to 0 degrees Celsius. We can use the specific heat of ice to calculate the amount of energy to warm the ice cube. Part B. When the ice reaches 0 degrees Celsius, the ice-water mixture remains at that temperature, even though energy is being added, until all the ice melts to become water at 0 degrees Celsius. We can use the latent heat of ice to calculate the amount of energy required to melt 1 gram of ice at 0 degrees Celsius. Part C. Between 0 and 100 degrees Celsius, no phase change occurs. The energy added to the water is used to increase its temperature, as in part A. We can use the specific heat of the water to calculate the amount of energy to warm the water from 0 to 100 degrees Celsius. Part D. At 100 degrees Celsius, another phase change occurs as the water changes to steam at 100 degrees Celsius. As in part B, the water-steam mixture remains at constant temperature, this time at 100 degrees Celsius, even though energy is being added, until all the liquid has been converted to steam. We can use the latent heat of a vapor to calculate the amount of energy required to convert 1 gram of water at 100 degrees Celsius to steam at 100 degrees Celsius. Part E. During this portion of the curve, as in parts A and C, no phase change occurs. So all the added energy goes into increasing the temperature of the steam. The energy that must be added to raise the temperature of the steam to 120 degrees Celsius is calculated as follows. Total amount of energy that must be added to change 1 gram of ice at minus 30 degrees Celsius to steam at 120 degrees Celsius is the sum of the results from all 5 parts of the curve. This exercise will help you better understand the theory.